Welcome to the talk, Bootstrap Inference Made Easy. My name is Måns Delin. My background is in academia, but these days I mostly work as a freelance consultant. I'm the author of the book Modern Statistics with R, and the creator of several R packages, including the boot.pval package that I'll be talking about today. So let's introduce the Bootstrap, starting somewhere else. If you've taken a course in mathematical statistics, you will have seen at some point how classical parametrical tests in statistics are derived, like the t-test, for instance. In classical statistics, we start with making some distributional assumption, for instance, assuming that our data comes from a normal distribution. From this, we use mathematics to derive the distribution of the test statistic, which might, for instance, concern the difference of the mean values of two groups in the case of a t-test. We get some formula for that, and a formula describing this density curve here. And then finally, we can compute the p-value as the area under some region of that curve. And this might work well. It might work really well, but sometimes this approach fails. And one situation where it can fail is if those distributional assumptions in step 1 are wrong. If the actual distribution of our data doesn't look like this hypothesized distribution, then the derivations in the second step and the p-values in the third step might be in error because our starting assumption was wrong. And so we can't always trust p-values and confidence intervals that we get from these classic parametrical methods. The Bootstrap is a tool that seeks to address this. It was introduced in 1979 by Efrons. It's been around for a while, and it starts not by looking at some theoretical distribution, but by looking at the empirical distribution of our data. What does the distribution of the data actually look like? From this, we can then derive the distribution of the test statistic using simulation. We simulate new samples from this empirical distribution by drawing samples from it, and then we get many observations of the test statistic and get an accurate approximation of the distribution of the test statistic. And then finally, we can compute p-values in a manner similar to that we would if we had a formula describing that distribution. We can also get confidence intervals in the same way. The test we're carrying out is still a t-test if a t-test is what we're doing, but it's no longer sensitive to the distributional assumption. So we don't need to worry about, say, normality. This has been available in R for a long time using the boot package. This allows us to compute bootstrap confidence intervals, but it requires us to write custom functions even for simple tasks like a t-test or regression coefficients, tests for those. And in addition, getting p-values can be tricky because the theory for the bootstrap dictates that if you want to compute a p-value, you need to do that sampling in the right way, using the null distribution of the statistic and so on. And it becomes a little tricky and a little technical if you try to do this. So my aim when I developed the boot.pval package was to make this easier. You should be able to compute a bootstrap p-value in one line of code, at least in standard cases. This package is built on top of packages like boot, car, LME4, and survival, so some of those workhorses of statistics. It allows you to write custom bootstrap tests if you like. So if you have some custom statistic and want to do a bootstrap version of it, this is the package for you. But it also has convenience functions for some things like tests of location and coefficients of regression models. So some standard things that are used a lot. There are different methods for computing confidence intervals using the Bootstrap with names like percentile intervals, studentized, BCA, and so on. All of these are supported in the boot.pval package, and they give slightly different results. The package makes sure that the p-values that you get and the confidence intervals that you get are in agreement. This isn't the case everywhere. For instance, if you do bootstrapping using the tidy models package, then the default choices give you p-values that aren't in agreement with the confidence intervals. So the confidence interval and the p-value might give different answers to the same question, and we don't want that. So in this case, you'll always get confidence intervals and p-values that are in agreement. You can use any of these methods. The convenience functions try to use reasonable defaults. So let's look at an example of how this package is used, starting with the t-test. In base R, we can use the t.test function to perform a classical student's t-test comparing two groups. In this case, I'm using the sleep data, where I want to compare two groups defined by the group variable, and the variable for which I wish to compare the mean values is the extra variable. So there's one way to write this code. You can do it using pipes as well if you like. then you need to use a placeholder for the data to indicate that the data that goes here is what we had on the left-hand side of the pipe operator. Either way, regardless of how you use this, the output will look something like this. A two-sample t-test, p-value is 0.08, and there's a 95% confidence interval for the difference in means between these two groups, and so on. And that's a classical student's t-test. It relies on the assumption of normality. If you don't have normal data, then, well, maybe it would work if you have balanced group sizes. If you don't, you might be in bigger problems, and so on. But you can use a Bootstrap t-test instead. And using the boot.pval package, what you have to do is that you have to, well, load this package. And then in a single line of code, you simply replace the t.test function with the boot t-test function, provide a model formula. No need to use that placeholder because this has been designed to work with pipes. And from this, you get the output for a Bootstrap t-test. By default, it uses a studentized confidence interval and the corresponding p-value. So you get your Bootstrap p-value, you get your Bootstrap confidence interval. The output looks identical to that from t.test, except that the Bootstrap has been used instead. In addition to this, there are convenience functions for tests of regression coefficients from different kinds of regression models. You start by fitting your regression model. Here I fit a linear model using the GLM function, specify the model formula, specify the data set I'm going to use, and then I run the boot summary function, which gives me a Bootstrap summary of the results. What it gives me is this data frame that we see here. One column, estimate, contains the beta coefficients from the model. Those are the estimates from the model, not at all affected by the Bootstrap. And then we have confidence intervals, lower and upper bound for those, computed using the Bootstrap, and p-values computed using the Bootstrap. You can also get this in a different output format. If you don't want this data frame, you want something that's ready for publication, you can pipe this to a function like summary to GT, which creates a summary table in a GT format. We also have flex table available here if you prefer that. So you can get this in a publication ready format with another line of code. This boot summary function, it works for linear models, but also for generalized linear models, mixed models, models from survival regression like Cox regression and AFT models, and some robust regression models and so on. So there are many different models for which this function works, and it will give you confidence intervals and p-values based on the Bootstrap. In addition to this, you may want to create custom tests for some other statistics not covered by these convenience functions. That involves writing a function for computing the Bootstrap statistic. So you write that function, you define how the statistic is computed for your Bootstrap sample. Then you use the functions boot and boot.pval to first run the bootstrapping step and then compute the p-value from that and get a confidence interval that's in line with the p-value. A fully worked example of this is found in the documentation for the package. So if you want to learn more about how to do this or learn more about the package, I recommend that you have a look at the documentation. It contains plenty of examples. So that's first on my list of further reading. You can also have a look at my book, Modern Statistics with R, where there are plenty of examples of how to apply this to different kinds of regression models. And if you want to learn more about the Bootstrap, I recommend the book by Davison and Hinckley from 1997, which covers the practice of the Bootstrap. If you want to go into the theoretical details behind it, I highly recommend the book by Peter Hall from 1992, which covers all of those nitty-gritty mathematical details. And that's all from me. Best of luck with your analysis, and I hope that you find boot.pval useful.
Well, thank you very much. We have a minute or two if there's a question or two. Yeah. Can you tell me can you tell us quickly a specific problem that you've used this on that demonstrates its great value?
Absolutely. I've used this a lot with biomarker data that frequently is non-normal even after a log transform. And if, say, I want to do something like a t-test or a regression where I'm concerned about the mean, and then many methods either assume normality or ask you to use something else that is not concerned with the mean. And then in this case, Bootstrap methods like this, like a t-test or a Bootstrap regression is a really good choice, I think, because it allows you to do inference about the mean, even in presence of strong non-normality. So lots of examples in proteomics and metabolomics and so on.
Mm-hmm. Yeah, where the data are highly non-normal and assumptions of normality will almost surely lead you astray.
Absolutely, yeah.
Good. Yeah. Anyone else? Okay. Well, in that case, let's thank the speaker for a very illuminating talk. And I think we'll close up this room and see you in the room for the next talk in just a minute. So thank you.
Thank you.